Happy weekend, greetings, and warm welcome to dear precious audience. Here we are again on another episode on professional masterclass under education for all, and our research topic is research design and methods. And today we will be doing our lecture 13, that is introduction to data analysis. We normally have it on Thursday, but due to some um, unforeseen situation, that we have to do it today on Sunday. So next week we will come back on Thursday. For this, I would gladly welcome our Ambassador Professor Dr. Rania Lampu to start the session. She's from Greece, and she's not a stranger to all of us. So I welcome Dr. Rania.
Thank you. Thank you so much. Good afternoon and good evening from Athens, from Greece. We have a very hot summer here.
Oh.
And yes.
What's the temperature there?
Over 40 degrees.
Oh my God. It's still so high, so hot.
Yes.
Okay.
So it's my pleasure to welcome you all to this session on introduction to data analysis. And it's more relevant, I think, than ever, because we live in a world overflowing with data. And data itself is just raw material, of course, but the real value lies in analyzing data, interpreting data, and drawing meaningful conclusions from it. And that's what data analysis is all about, turning information into insight and insight into action. So over the course of this session, we will be taking our first steps into this fascinating field. You will learn what data analysis means, the key concepts involved, the tools, amazing tools commonly used, and how to apply simple yet powerful techniques to real-world problems. Because more than just numbers and charts, data analysis is about curiosity, logic, and storytelling. And today you're starting a journey that could open doors in industries ranging from healthcare and finance to sports, education, and beyond. So once again, welcome. I would like to extend my heartfelt thanks to Elga de Higher Education and of course Dr. Esther Mala for inviting me to conduct this series every week on research, very valuable and precious sessions. And now we'll start sharing my presentation. No.
Yeah, she got disconnected. I think she will come back again. Just give a few minutes, the audience. Sorry for that. And now we start sharing my presentation. Okay. Yeah. You can upload your PPT.
Can you see now my presentation, Dr. Esther?
Yes, you can try moving your slide. It's visible.
It's visible. Okay, thank you. So first we need to start by understanding data basics. So what is data, first of all? Data is information which is collected, observed, or measured and recorded for reference or analysis. So it's something that represents facts, statistics, or values that can be used in order to describe, to understand, or predict a phenomenon. We have two different types of data. So many times we have discussed about these things, about qualitative and quantitative data, about numerical and non-numerical data. And what about now the difference between structure and unstructured? So the difference between structured and structured data lies in how the data is organized, is stored and processed. When we talk about structured data, data is here is organized in a predefined format, typically is in rows and columns, like a database table. And what are the characteristics here? That structured data follows a consistent schema, names, dates, numbers. It's easily stored in relational databases. It's easy to search and analyze using tools. For example, customer databases for financial records or the sensor data, which includes the temperature, etc. And usually the tools used is SQL, Oracle, MySQL, etc. On the other hand, we have unstructured data that doesn't follow a predefined format like before. And this, of course, makes it harder to organize and analyze directly. So what are the characteristics here? That there is no fixed structure, that this requires pre-processing and advanced tools to analyze. It's often large, and some examples include the images, audio, video files, PDFs, chat logs, web pages. The tools used here include natural language processing, NoSQL databases, AI, ML models, etc. So we want to compare structured and structured data in terms of format. We can see here is a predefined, no predefined storage, relational databases. On the other hand, we have data lakes, file systems. In terms of searchability, the one is easily searchable. The other one requires advanced techniques. We mentioned about examples, structured data, names, sales records. Structured data includes video, social media, emails, and the tools SQL and NoSQL. Now, what is the difference now between data, information, and knowledge? That's a great question. Data, we mentioned that is everything that has to do with raw and processed facts and figures without content. The nature is unorganized, often meaningless on its own. And what about the analogy? Like individual letters or numbers which are scattered on a page. This is the analogy. On the other hand, what is information? Data that has been processed, that has been organized or structured to provide meaning. It's more useful than data because it answers who, what, where, and when. And the analogy here is that we talk about words from letters starting to make sense. And knowledge, the third definition is information that has been understood, is interpreted and applied based on the context. For example, knowing that the 98% is 98 degrees is a normal human body temperature and that no medical intervention is needed. This is example of knowledge. The nature is that it answers how and why, so we talk about actionable insight. And the analogy, it's a sentence or a story that conveys meaning and purpose. So what are the common sources of data? A common source of data can be grouped into several categories based on where the data originates and how it is collected. We have a primary sources of data, which actually their aim is specific. We talk about specific purpose. So surveys and questionnaires, that could be interviews, could be observations or experiments or sensors and Internet of Things devices, data from machines, wearable devices, etc. And on the other hand, we have secondary data sources, data that has already been collected and is reused. That could be government databases, the census data, academic publications, research studies, or company reports, industry reports. In other presentation, I mentioned that sometimes we talk about gray literature. Gray literature contains this one, secondary data sources. And digital and online sources, it's data which is stored online, generated and stored online. And this includes, of course, websites, social media platforms, search engines, e-commerce platforms, etc. The transactional sources, data generated by business operations, point of sale systems, CRM systems. So, for example, here, customer interactions in history. If we want to give an example, the ERP systems, for example, supply chain, finance, human resource data. And we have machine-generated data, which is automatically created without human input. That would be logs, security logs, for example, telemetry, usage and performance data from devices, clickstream data, which has to do with the user activity on websites or apps, and cloud and CAS platforms, which is data which is stored and processed via third-party services, for example, Google Analytics or Salesforce, HubSpot, Azure Logs, etc. Azure, here we work on this in the Greek Ministry of Education, has to do with infrastructure usage and performance. So, data collection now. Data can be collected using actually various methods depending on the type of data, qualitative or quantitative, the research goal, and the context. These methods fall into primary and secondary categories, as I mentioned before. So we have the surveys, which is a structured set of questions. So that could be qualitative or quantitative. Examples could be political polls, interviews on one conversation, which is mainly qualitative. Examples, employee feedback or in-depth opinions. Observations, both qualitative or quantitative, when we try to watch two subjects in natural or controlled settings. Experiments, always about control test here, testing, so quantitative, in laboratories. Focus groups, qualitative mainly. For example, it's about group discussions, which is guided by facilitator in marketing research, and sensor data logging, which uses devices to automatically capture data, Internet of Things sensors or fitness trackers or satellite data. So the primary data contains this, and the secondary data, when you use data already collected by others. For example, existing databases, quantitative, that would be government records or research institutions, the literature review, which actually may come from books, from articles, from reports, so usually it's qualitative. And web data mining, when we extract data from websites, from social media or APIs. So this is always about online platforms and forums, data type, both qualitative and quantitative. So choosing a method depends on research goals, on time and budget, of course, availability of subjects or data, and required data accuracy and depth. So what is the difference now between primary and secondary data? The difference lies in how the data is collected and who collects it. Data collected first-hand by researcher, organization for a specific purpose, this is primary data. So what the characteristics is that it's original and collected directly from the source. It is tailored to the specific research question, and often primary data is more accurate and up-to-date, but time-consuming and costly. For example, surveys and questionnaires, the interviews, sensor or IoT data collected directly from devices. For example, give an example, a company conducting its own market research to understand the customer preferences. On the other hand, secondary data is data that has already been collected, processed, and published by others for a different purpose. It is available through existing sources. It's more cost-effective and quicker to obtain. May be outdated. This is the main disadvantage. It may be outdated or not perfectly suited to current research needs. Examples, government reports, census data, or academic research papers, or market research reports from third parties, or news articles or company financial statements. For example, a student who uses World Bank data to study global economic trends. So this is the comparison table, more or less. We could say that primary data is original, specific, and tailored, but takes more effort. Secondary data is pre-existing, faster, and cheaper, but may not fit perfectly. Both are useful depending on the goals, on the gadget, and timeline of the project. Now, the difference between service and experiments in data collection. Both they are commonly used in data collection, but they differ significantly in purpose, design, and how they collect and interpret data. So we can see here that servers are used to gather self-reported data or opinions or behaviors, talk about descriptive, usually data, what people think, the approach observational and interventional, the control of variables is low because researchers observe but they do not manipulate variables. The setting is usually a natural setting, and the causality that cannot establish causation, only correlation. And then they had experiments. Experiments try to define cause and effect relationships between variables. The data collected is about measured effects of manipulated variables. It's control and interventional, high control over variables because researchers can manipulate and control others. And a lab test, for example, where students use a new study technique to see its effect on exam scores. Control settings always, the causality is to establish cause and effect relationship. So in summary, we could say that surveys are best for gathering opinions, behaviors, and attitudes from a large group. Experiments are best for testing hypotheses and causal relationships under controlled conditions. What is data scrapping and how it is used is also called web scrapping. Is the process of automatically extracting information from websites or other digital sources. It involves using software tools or scripts to collect structured data from unstructured or semi-structured sources like HTML pages. And how it works, the scrapper sends a request to a web page. The server returns the HTML content, so download HTML, parse the data after. The scrapper extracts specific information, it will be a job listing, and then we store the data. The extracted data is served in a usable format like a CSV, etc. So what are the common uses of data scrapping? In market research, for example, we use it for the collect pricing of the product listings. For job application, we can gather job postings from various job boards in a single platform. We can extract property data like prices, location, availability. We can pull headlines from multiple news sites. We can scrape posts on social media, for example, use comments to analyze sentiment or trends. We can extract data and research from online publications or data sets or public registries. And of course, financial analysis, we can collect stock prices or financial news reports from finance sites. So what are the ethical considerations here is that many sites prohibit scrapping in their terms of service. This is the first one, very important. That the use of scrapping should always comply with the rules like GDPR in the European Union, the rules of protection of data, and sites may use robots.txt files to indicate which parts of a site can or cannot be scrapped. The common tools and libraries for this is a beautiful soup, Python, scrapping Python, a full feature scrapping framework, Selenium, Puppeteer, etc. Now, for data cleaning and pre-processing, first of all, what is data cleaning? Data cleaning is the process of detecting, or correcting, or removing inaccurate, incomplete, inconsistent, or relevant data from a data set. Why it is important? Because it guarantees that this data is reliable, accurate, and ready for analysis or model training. So why it is important? Because it improves accuracy. Dirty data leads to wrong conclusions. It reduces errors, so it prevents outliers, typos, duplicates, and missing values. It enhances model performance, very important, because clean data leads to better predictions and analysis outcomes. It saves time and money because fixing problems, we can fix problems later, is more costly than cleaning early, definitely. And it improves data usability because clean data can be shared, reused, and trusted across teams. The common data cleaning tasks are related with this, are this one, how to handle missing values, This has to do with how we estimate and remove empty fields, how to remove duplicates, so delete repeated entries, how to correct errors, how to fix wrong formats, standardize data, ensure consistent labels, how to filter outliers, identify and deal with extreme or abnormal values, and how to validate formats to ensure emails, IDs, all these follow expected patterns. So the clean data means trustworthy insights. Whether you are training an AI model or making business decisions, clean data is essential. And usually another issue problem is how we can handle missing or inconsistent data. Handling missing or inconsistent data is a critical step in data preprocessing to ensure analysis and models are reliable. So what are the common techniques and best practices? First, we need to identify and understand the problem. So detect missing values using methods like is null in Python pandas or summary statistics. We can check for inconsistencies. We can understand the pattern of missingness. This includes missing completely at random or missing at random or missing not at random. The second step and best practice is handling missing data, which has to do with deletion methods. That could be list-wise deletion, so remove rows with missing values, or column deletion, remove columns with too many missing values. Then imputation methods, replace the missing values with mean, median, or mode. This is another best practice. Forward or backward fill, so use previous or next valid value. Interpolation, estimate missing values based on neighboring data points. Predictive imputation, use regression or machine learning models to predict missing values. Multiple imputation, we have when we try to generate imputed data sets and average results to reduce bias. And of course, flagging missing data is when we try to create a binary indicator variable that can actually flag missing values to preserve information. Now, how we can handle inconsistent data? First, we can standardize the formats, we can correct the misspellings, we can resolve conflicting errors with data cleaning. The normalization, when we try to convert the categorical data to consistent categories, and the outlier detection is when we identify and review unusual values that may indicate errors. The documentation and validation, when we try to document all cleaning and imputation steps for transparency. Then we validate the clean dataset by checking the summary statistics. So the missing data, the common solutions is deletion, imputation, flagging. And for inconsistent data, the common solutions are standardization, correction, and outlier handling. So what are the final tips? That we need always to explore the data first to understand missingness patterns. Then choose methods based on data type or missingness mechanism and project goals. After, we need to consider multiple imputation or predictive models for complex cases. Always be cautious about bias introduced during imputation. And what are outliers and how they can be detected and treated? Outliers are actually always data points that are significantly different or distant from the majority of data. They don't fit the general pattern, and they can alter results or indicate important variations. How can outliers be detected? It can be detected through visual methods. So, for example, box plots, scatter plots, or histograms. Also statistical methods. The z-score. The z-score measures how many standard deviations a data point is from the mean. So data points with the z-score is more than 3 or less than 3. The ones 3 are often outliers. And in the quartile range, this is another statistical method that we can use to detect outliers. And of course, we have the software tools, statistical software. We have built-in functions to identify outliers like R and Python. How we can treat them outliers? We can investigate means to verify if it's a data entry error or for extreme value. We can remove it if it's an error or irrelevant. We can remove it. We can transform data to reduce the impact of outliers. Or we can use robust methods. We can use techniques less sensitive to outliers, like use a median instead of mean. And keep it analyzed separately. Sometimes outliers contain valuable information, so we should analyze them separately. Now, what is data normalization and data standardization? These are two common techniques used in data preprocessing to prepare data for analysis or machine learning, and these help make data consistent and comparable. So first, data normalization is when we rescale data to fit within a specific range, usually from 0 to 1. Why? Because we want to ensure that different features have the same scale. And how? This is usually here we try to use the min-max scaling formula. For example, if a data set values range from 50 to 200, normalization will convert this to a range between 0 and 1. I think this is clear. Of course, we need to use a specific formula that I mentioned before, min-max scaling formula. And on the other hand, data standardization, when we want to transform data to have a mean of 0 and a standard deviation of 1. This is also what we call Z-score normalization. Why it is useful? It's useful when data follows a normal distribution or where algorithms assume that data is centered. So what are the key differences between them? Is that normalization, here the output range is typically between 0 and 1. Standardization, here you can see the difference for mean and deviation. Standard deviation is 1. The use case when normalization, where data needs to fit a bounded range. For standardization, where data distribution matters. And what's the effect of distribution? The normalization does not change the shape of distribution. In data standardization, centers and scales data distribution. So these are the main differences. Now, something else very important is what we call exploratory data analysis, and why this is important in data analysis. First, when we talk about exploratory data analysis, is the process of investigating and summarizing a data set in order to understand its main characteristics, often using visualization, statistics, or simple transformation before applying formal modeling or hypothesis testing. So why this is important? Because it helps us understand data, it reveals patterns and trends in relationship, it helps us detect issues, so it helps spot missing values or outliers early, it helps us guide modeling, it informs the choice of algorithms, features, and transformations, it helps us validate assumptions, so it checks if data meets assumptions required for analysis, and it assists in communicating insights, so here we can share findings clearly with stakeholders thanks to visualization. The common EDA techniques are this one, the summary statistics, data visualization, the correlation analysis when we try to measure relationships between variables, a distribution analysis, we check if data follows normal distributions, and missing data patterns when we identify gaps or inconsistencies. Some common techniques, it's about distributed statistics. Actually, exploratory data analysis, it's all about understanding your data through various techniques before building models. So descriptive statistics first, which includes, it's very well known, measures of central tendency, mean, median, mode, the measures of dispersion, variance, standard deviation, range, etc. And summary statistics, they count mean, max, percentiles, and so on. And with data visualization, histograms, box plots, scatter plots, bar charts, heat maps, pair plots, we're going to explore this in the end. I will show you some photos also, to understand the difference between these different categories and different techniques. So data cleaning and handling missing values. Here we try to identify missing values. We check for duplicates and consistencies. We design an imputation or removal of missing data points. The correlation analysis, when we calculate the correlation coefficients of Pearson or Spearman to find relationships between variables, and we try to detect multicollinearity among predictors. The dimensionality reduction for large data sets. So techniques like PCA, principal component analysis, is used to visualize high dimensional data in 2 and 3 dimensional. And univariate and bivariate analysis. Univariate has to do with study distribution of one variable, and bivariate when we study the relationship between variables. Outlier detection, I mentioned before, when we use statistical methods here or visualizations to find extreme values, the feature engineering ideas try to create new variables based on existing ones. Here the goal is to find hidden patterns. So a summary table here could be that with descriptive statistics, we try to summarize certain tendencies and spread. The visualization of explored distributions, where we can use Seaborn, Plotly, Matplotlib, many tools now have AI tools also at our disposal. For the missing data handling, the purpose is to identify the missing values, so the tools are deletion or imputation. For the correlation analysis, we understand variable relationship and we use heat maps or correlation matrices and many other techniques. Dimensionality reduction and outlier detection, where you try to detect anomalies through box plots, z-score, etc. So what types of plot are used to understand data distribution? Here is the histogram, which shows the frequency distribution. The box plot displays summary statistics outliers. The density plot estimates the probability density function. The dot plot shows individual data point. A stem and the leaf plot shows data distribution with actual values. And the bar chart, which actually compares categories or groups. And this one is useful, a bar chart when data is categorical to show count or proportion. Dot plot is useful for small data sets. Stem and leaf plot is useful for small data sets also. And the density plot is useful when we want to see the overall shape and comparing distribution. So how can correlation between variables be explored? What we can do here is that to say that exploring the correlation between variables helps us understand how two more variables relate to each other, whether they move together inversely or not at all. For example, for visual methods, we have scatter plots. Here we plot two variables against each other. Patterns like upward or downward trends suggest positive or negative correlations. The heat maps visualize correlation matrices where color intensity shows the strength of correlation among multiple variables. And pair plots, scatter plots matrix, shows scatter plots for all pairs or variables in a dataset, which is useful for spotting relationships. Then statistical measures, the Pearson correlation coefficient, which measures the linear correlation between two continuous variables. The Spearman's rank correlation, which measures what? It measures monotonic relationships, not necessarily linear, based on rank data. It's good for ordinary variables or non-linear trends. And Kendall's, though, it's another rank-based correlation often used for smaller data sets or when data has many ties. The correlation matrix, when we try to calculate pairwise correlations for all variables in a data set, it can help us to see how variables interact and is often visualized with a heat map. More advanced techniques, partial correlation. Partial correlation measures correlation between two variables while controlling for the effect of other variables. The cross correlation is used in time series data to explore correlations and different time lags. Tools and libraries with Python, for example. Or Excel, scatter plot charts. So many tools for this. And for descriptive statistics, that we need to know these things, the measures of central tendency. Measures of central tendency are all these statistical values that describe the center point or typical value of a data set. They give a single value that summarizes the entire data. So the three main measures contain these. Measure the mean, the average, the sum of all values divided by the number of values. Median, what is median? The middle value when data is ordered. And the mode, the value that appears most frequently. So mean average means when is used when data is symmetric, has no extreme outliers. Median is used when data is altered or has outliers, and mode is used for categorical data or when we want to find the most common value. Here you can see how to calculate this. Median, we have ordered data, etc. I think this is things that we already know, more or less. And why they are important? Because mean gives a balanced average but sensitive to outliers. Median provides a robust center value, less affected by extreme values. And mode shows the most common category or number useful for understanding frequency. So we could say that mean is best for numeric, for symmetric situations in data, median for skewed data, and mode for categorical data. Now, what are the measures of dispersion? Measure for dispersion describe how spread out or scattered the data points are in a data set. And this helps you understand the variability or consistency of the data. So the common types are range. So range, what is the difference between the maximum and minimum values in the data set. This gives a quick sense of the total spread, but it is sensitive to outliers. Remember this. Variance, it's the average of the squared differences between each data point and the mean. It measures how data points deviate from the mean. Larger variance means more spread. The standard deviation, this is the square root of the variance, of the variance, and this is expressed in the same units as the data, make it easier to understand than variance. So here, why use this? Because actually range is simple but limited. Variance is fundamental statistics and used in many models. And standard deviation is most, we could say, intuitive measure of spread. How do you interpret now a skew distribution? So the type of skewness is, first we have, first, what is a skew distribution? Skew distribution is a probability distribution where the data is not symmetric, meaning it leans more towards one side. So the type are usually this, right skewed, which is possibly skewed. For example, income distribution, where most people earn average or below average, but if you have very high incomes. So here you can see what is the shape. And the mean is bigger than median, median bigger than mode. On the other hand, we have negatively skewed distribution. Here, mean is less than median, median is less than mode. So here, how we can see here, how we can interpret this, that most data points are concentrated on the right, higher values, but some unusually low values pull the mean to the left. What are the implications of skewness? That measures of central tendency differ more in skewed distributions. Mean is pulled toward the tail and can be misleading as a measure of central tendency. Median is often a better measure of central tendency in other data because it's less, of course, affected by extreme values. And skewness affects statistical analysis and assumptions. Now, how we can summarize categorical versus numerical data? Summarizing categorical numerical data involves different techniques because they represent different types of information. Categorical data represents categories or groups. For example, frequency count, the number of occurrences of each category. Here we can see, for example, the color, proportions or percentages. The mode is the most frequent category. The cross tabulation, which shows the relationship between two categorical variables, the visualization via bar charts, bit charts, etc. So this has to do with categorical data. On the other hand, numerical data consists of numbers that can be measured or counted. Measures general tendency that I mentioned before, mean average value, median middle value when data is sorted, mode, the most frequent value. The measures of dispersion that I mentioned also before, the shape of distribution, skewness is the symmetry of data distribution, the kurtosis means thickness of distribution. Visualization, here you can use box plots, density plots, histograms, etc. This is more or less the difference. For data now visualization, we have very nice tools for this. Data visualization, of course, is the process of representing data graphically using charts, graphs, maps, and other visual tools to make complex data easier to understand and interpret. So what are the key reasons data visualization matters? Because visuals help people quickly grasp patterns and outliers that might be hidden in raw data. It speeds up decision making, it enhances memory and recall. Visual, of course, is easier to remember than raw numbers. Facilitates communication because it bridges the gaps between technical experts and non-experts, and reveals hidden relationships because complex relationships or clusters become visible through plots or heat maps. And of course, supports storytelling with data. Visual narratives help persuade and explain findings effectively. So the common types of visualization is here what we can see some examples: bar charts, pie charts, other charts, bubble charts, DONAF. Here, okay, so we have for each one the corresponding photo. The bar chart, when it's used, is used to compare quantities across different categories. Histogram to show the distribution of a single numerical variable by grouping data into bins. It's useful for understanding frequency and spread. This is vertical or horizontal. The line chart, it's great for time series data when we display trends over time for all the categories. The scatter plot, when we try to show the relationship between two continuous variables, the height or weight, for example. We use it for spotting correlations of clusters. The pie chart, which is best with few categories. We use it for showing proportions of a whole. The box plot, which is useful for spotting outliers. And we try here to summarize the distribution of a data set. For example, we want to compare the scores across classes. The heat map, it's great for spotting patterns of clusters. And here we try to show magnitude of values across two dimensions using colors. The area chart, it is used for showing cumulative quantities over time. Here we can see that it's similar with the line chart, but it's filled in order to emphasize the volume. The bubble chart, which is used for showing relationship between three variables, and it is useful for multivariate visualization. And the stack bar chart, which shows parts of a whole across categories with segments stacked. So here this helps compare both total and subgroup of values. So here is a comparison table, quick summary table, bar chart. With bar chart we compare categories. when, for example, use case product sales, the histogram, distribution of numerical data for the age distribution. The line chart shows trends over time. For example, the website traffic over months. For website traffic over months, you will use line chart. The scatter plot shows the relationship between two variables. The pie chart proportions of a whole, for example, the market share. The box plot shows the data distribution at outliers. The heat map, the patterns across dimensions. So here, an example use case correlation matrix. The area chart shows cumulative trends, the revenue growth, for example, and relationships with three variables. And stack bar, of course, part to hold comparisons across groups, sales by product and region. And how does visualization help identify trends and outliers? Because we can identify trends through tools like line graphs, scatter plots, I mentioned before, make it easier to see patterns or trends over time. Trends could be upward, downward, also which shows the growth or decline, seasonal or cyclical changes. We can spot outliers because visualization like box plots or scatter plots or histograms clearly highlight data points that deviate significantly from the rest. Outliers appear as points far away from clusters or outside typical ranges. So they stand out visually, can be quickly identified unlike in raw data tables. And of course, visualization is powerful because complex data sets become easier to understand quickly because humans are better recognizing shapes and clusters of pattern recognitions visually than in numbers. And early detection of trends can guide further analysis. So it supports decision making. What tools are usually leveraged for data visualization? The Spreadbar software, Microsoft Excel, Google Sheets, Tableau. These are most popular ones for business. Is Tableau is Power for BI. Looker, it's a cloud-based BI platform. Python libraries, of course. Matplotlib, Seaborn, Plotly, Altair, are libraries. Other tools also like ClickView, etc. And now a little bit about inferential statistics. The difference between descriptive and inferential statistics is that both descriptive and inferential statistics are key parts, of course, of data analysis, but they serve very different purpose. Descriptive statistics tries to summarize and organize data so it can be easily understood. So descriptive statistics describes what the data shows. The tools we can see here, the graphs, the charts, and the tables. The scope applies only to the data set at hand. For example, in a class of 30 students, the average test score is 85. We're only describing here the known data. On the other hand, with inferential statistics, we try to draw conclusions beyond the immediate data. So this includes hypothesis testing, this includes confidence intervals, regression analysis. We can use t-tests, ANOVA, t-square tests, and this means that we can make inferences about the population from a sample. To give you an example, based on a survey of 500 people, you predict that 60% of the entire population prefers this product. This means that we are making inference about the larger group. It's not description anymore. So inferential statistics makes predictions or inferences. The data uses sample of population. With the descriptive statistics, we have the entire data set. The output is presented through graphs, averages, and summaries in the descriptive statistics. Inferential statistics, we output hypothesis, estimates, and predictions. And with descriptive statistics, we don't have generalization as we have with inferential statistics. What is hypothesis test? Of course, is this statistical methods, what is used to make decisions or inferences about the population based on assembled data, as we mentioned before. It helps us understand whether a certain assumption about population parameters is likely to be true. Here, the key concepts that are necessary, absolutely necessary to know, is null hypothesis. When we say, for example, there is no difference in test scores between two groups. This is a null hypothesis, the default or starting assumption. And alternative hypothesis, what you want to prove or test for. There is a difference in test scores. This is alternative hypothesis, what we want to test. The steps in hypothesis testing always include these following stages. How you state the null and alternative hypothesis. You choose the significance level. The common choices are this one, 0.05, 0.01. It's the probability of rejecting the null hypothesis when it's actually true. And then we select and perform a test based on the data type in question. When we calculate the p-value, what is the p-value probability of observing your result if the null hypothesis is true? Then you compare p-value to A, the significance level. If the significance value is less than the significance level, the p-value is less than significant level, then the evidence support the alternative hypothesis. If the p-value is larger than the significance level, this means that it fails to reject the null hypothesis, so it's not enough evidence to support alternative hypothesis. So the first things, I think the elementary things that we need to know about hypothesis testing. We need to be familiarized with these concepts and know, of course, about the test types. The test when we try to compare the means, ANOVA, when we try to compare means of 3 and 4 groups. The T-square test, we try to test relationship between categories. The Z-test, when we compare proportions or large samples. And the man with U, a test which is alternative to T-test. So here we need to know these terms that I mentioned before. Null hypothesis, alternative hypothesis, the p-value, it's the probability result occurred by chance. The significance level, reject the null hypothesis and fail to reject the null hypothesis. The confidence intervals and p-values, which are very important things that we need to know. Confidence interval gives a range of values that is likely to contain a population parameter based on simple data. For example, a 95% confidence interval means that we are 95% confident that the true population value lies within this range. This uses estimation population parameters, assesses the precision of estimates. P-values tells you how likely it is to observe your data, assuming the null hypothesis is true. So the null hypothesis, remember, is always a default assumption. There's no effect. A small p-value suggests that the observed effect is unlikely under the null hypothesis. The large p-value suggests that there is not enough evidence to reject the null hypothesis. For example, if we want to test whether a new drug is better than a placebo, and with a p-value of 0.02, this means that there is a 2% chance of seeing the results if the drug actually had no effect. This, of course, would lead you to reject the null hypothesis. And some common misunderstanding is here that the p-value is not the probability that the null hypothesis is true. It does not measure the size of an effect, just the evidence against the null. Here you can see the comparison also table. Some tools and technologies, statistical analysis tools, SPSS. We can dedicate one session for this. We can show how SPSS works step by step. Stata, SAS are the data visualization tools that I mentioned before, the data management tools, SQL databases, and Vivid's an amazing AI tool for quality data analysis. We can also dedicate a session for this. Atlas Teach also very nice tool, AI tool. It contains also predictive analytics. It's for qualitative data. MATLAB, Jasper, more specialized tools. Each one has its strengths and weaknesses. We can't say that one is better than the other. And the real-world applications now, for example, data analysis used in business direction making, sales, marketing. In customer insights, we want to analyze behavior preferences to improve experience, financial planning, to track expenses, to forecast revenue, for operational logistics, for product development, for performance monitoring, to evaluate our employees' performance, for retailing, for banking. For banking, we can use predictive analytics to detect fraudulent transactions. Healthcare, AI's use is very useful also for all these things. For decision type, strategic long-term, the data we use is forecasting models, market trends. For tactical mid-term, we can use ROI analysis, return on investment analysis, department performance. Operational day-to-day data uses real-time metrics, sales reports. And of course, data analysis play a crucial role in healthcare, in finance, and marketing, and all these domains. Because it can transform actually raw data into actionable insights across these industries. In healthcare, we can help us analyze patient data, we can monitor vitals, we can reduce wait times, operational efficiency, we can help us with public health monitoring, with personalized medicine. In marketing, we can identify target audiences, we can recommend products based on purchase history. The churn prediction, what is churn prediction? When we identify customers at risk of leaving or triggering retention strategies. Our market trend analysis, when we track competitors, seasonal trends, and consumer sentiment. With finance, this helps us with analyze transaction patterns. We use historical data to optimize investments or portfolio management. With risk assessment, of course, when we try to predict the market volatility or operational risk, with regulatory compliance, etc. So, data analysis is useful not only for these domains, of course, but for every domain. And ethical considerations, of course, are there, are critical to ensure that data is used responsibly, fairly, and without harm. So do not share or expose personal information, use encryption, anonymization, or masking where it's necessary. Follow the data protection laws like GDPR I mentioned before. Data should be collected with the knowledge and permission of the people involved. Ensure that data collection are free from prejudice and free from bias. Be cautious of reinforcing stereotypes through skewed data. Don't manipulate data to mislead or produce a desired outcome. So this means report findings honestly, including limitations and uncertainties. It's not a weakness to acknowledge limitation. We should always acknowledge the limitation of our research study, and avoid what we call cherry-picking data or using inappropriate statistical methods. Be clear about how data was collected and analyzed, document methods, sources, and decisions to ensure reproducibility and accountability. Be open to scrutiny and willing to correct mistakes. Acknowledge sources of data and give credit for other works, of course, and don't use proprietary or copyright data without permission. Always be mindful of responsible data sharing. Share data ethically only when it's appropriate, when it's anonymized and with permission. So you need to understand the consequences of releasing data out to the public. So ethical data analysis means protecting people, means ensuring fairness, reporting truthfully. Enter the limitations before concluding how data analysis are related with the quality of data. Remember the quote of AI experts who say that garbage in, garbage out, poor quality data can lead to misleading results. Data cleaning and validation are critical, of course, but they can be time consuming. The biases in data, sampling bias, selection bias can skew analysis. Correlation versus causation. Finding relationships or correlation doesn't prove one variable causes another. Very important difference. Is another thing correlation, another thing causation. Mistaking correlation for causation can lead to wrong conclusions always. The overfitting, underfitting. In predictive modeling, overfitting means that model is too closely tied to the training data and performs poorly on new data. And on the other hand, underfitting means that the model is too simple and misses important patterns. In limited context, data alone often lacks context, so understanding the domain and real-world factors is essential. Numbers don't capture everything. For example, numbers cannot capture emotions or cultural factors. The data privacy, of course, complex models like deep learning can be difficult to interpret. So stakeholders might find hard to trust or understand results. So in the question of complexity interpretability. Static versus dynamic data, because data often represents a snapshot in time, real-world conditions can change quickly. Models may become outdated if data is updated regularly. So thank you very much. I will stop here. And of course, for any question, I'm here to discuss.
Yeah, thank you. Thank you so much. Congratulations for completing it today. Okay. So I think this is the last topic for the intermediate level, right? So next week we'll be going to advanced level. Yes. So that's why I wish you congratulations to you and also to all our audience who had been following us. And we are super excited to continue to the next level. Yeah. So as usual, we'll have it on Thursday. And please look out for our ad on the social media. Thank you so much, dear audience. I'm very sure that you have gained much from the sharing today. And of course, you see her presentation are well defined, and the description is very good. You know, the diagrams are very clear. So I'm very sure that you have gained much. And of course, after this, we will upload in our YouTube. Our YouTube channel is Elegant Empire Education. Do feel free to watch, share, and like it. Thank you so much. So we'll meet again next week. Thank you, Dr. Rania, for this amazing session with you. Thank you for your time.
Thank you very much. Thank you.
Bye-bye.
Bye.